All right, next up is question number 3, and part A says to evaluate the integral of r dr d theta, where r varies from 0 to 2 secant theta, and theta is varying from 0 to pi over 6, by first converting it to rectangular coordinates. All right, so let's draw a picture of the region of integration, and I'm going to start with looking at r equals 2 secant theta. So first notice that secant is the reciprocal of cos. So I have 2 over cosine theta. And so if I multiply both sides by cosine theta, this is saying that r cosine theta is equal to 2. And in polar coordinates, r cosine theta is equivalent to just the x coordinate. So I'm saying, in fact, that this equation r equals secant is just describing the vertical line x equals 2. All right. And now theta is varying from 0 to pi over 6. So here's 0 and here's pi over 6. And so now for the integral, since theta is our outside variable of integration, we're going to think about fixing theta. And if theta is constant, that's just going to describe a line through the origin. So let's say this is my fixed theta. And now r is going to vary from 0, which is just at the origin, out to 2 secant theta, which is right here on this vertical line. And now we're going to let these blue sweeping segments here from 0 out to the vertical line to sweep through the angle from 0 to pi over 6. So what we're describing there is just this triangular region right there in the first quadrant. So I'll call that region R. All right. So now this integral is the double integral over the region R of what? Well, r dr d theta is just dA. So we're in fact just integrating dA over the region R, and we know from sections 14.1 and 14.2 that this is nothing other than the area of the region R. And since R is just this triangle, we can just find the area of the triangle using 1/2 base times height. And the base there is 2, and for the height, well, since this central angle here is pi over 6, I'm going to look at the tangent of pi over 6, and that would equal the height of the triangle divided by the base, which is 2. And so the height then would be 2 times the tangent of pi over 6. Tan of pi over 6 is root 3 over 3, so this would be 2 root 3 over 3. All right, so now putting all that together, the area of our region would be 1/2 the base, which is 2, times the height, which is 2 root 3 over 3. So that all simplifies to the 2 root 3 over 3. All right, great. Let's check out B next. This one is a little bit more complicated. Now this is integrals that are in rectangular coordinates, and we want to convert them to polar coordinates. And notice the integrand in each integral is the same, it's x. And in our first integral, we're letting y vary from the root of 1 minus x squared, and that's just the top half of the unit circle, up to square root of 4 minus x squared, and that's the circle centered at the origin of radius 2. And x, it's varying from 0 to 1 in the first integral, and then from 1 to 2 in the second integral. So altogether, it's going from 0 to 2. So go ahead and put these in for our reference. And so, as we said here in this inner integral, we're going from the unit circle, so I'll just draw this portion of the unit circle from 0 to 1, out to that circle of radius 2. So I'll just draw this portion, circle of radius 2. And so we're really describing now, it's a dy dx integral looking at a vertical strip like this, going from this inside circle here to the outside circle. Okay. And then we're going to stack these strips as we let x go from 0 to 1. So that's going to fill out this portion of this annulus from 0 to 1. All right, so we got this part, and then for the second part, pretty similar, but now we're going from 0 to the root of 4 minus x squared. So we're now going from the x-axis out to the root. So this is when y is 0, and this is when y is the root of 4 minus x squared. And we're going to stack these vertical strips as we let x go from 1 to 2. So we're going to be filling out this. Okay, so in fact, we really just have this annular region right here, and then of course that is really easy to describe in polar coordinates. In polar, we're letting r vary from 1 to 2, and we're letting theta vary from 0 to pi over 2. Okay, so putting this all together now, right, because we're going to combine these two integrals into just a single integral over this region. I'll call it R. And our integrand is x, and then dy dx. So what is x dy dx equal? Well, what's x? X is r cos theta. That's this part. And what's dy dx? This is dA, which is in polar r dr d theta. So you put all that together, and the x dy dx is in fact r squared cos theta dr d theta. Okay, so here, actually, instead of writing it as a double integral over r, what I'm going to do is just go straight to the bounds of integration, and then I can just do the calculation. So we're integrating r squared cos theta, and then we have our dr d theta, and r goes from 1 to 2, and theta goes from 0 to pi over 2. Cool. All right. So one thing to notice here is that this integrand is a product of an expression that depends only on r squared with another expression that depends only on theta. So we've seen this kind of thing back in 14.1 and 14.2. I can write this as the product then of the integrals 1 to 2. This is dr, and then 0 to pi over 2 cosine. This is going to simplify the calculation quite a bit. So here we got r squared, its integral would be r cubed over 3, going from 1 to 2. Integral of cosine is sine, and we're going from 0 to pi over 2. And this is going to give us 8/3 minus 1/3, that'd be 7/3. And evaluating at pi over 2 is going to give us the sine of pi over 2, which is 1. Evaluating at 0, the sine of 0 is 0, so this is just going to give us 1. So 7/3 is the value of these two integrals combined, right? And again, doing that calculation straight ahead would be rather cumbersome. Okay, so great, that's going to do it for this problem.